section 4.5, we're going to go back and look at the dimension of a vector space. So if you recall, back in chapter 2 we talked about this, but we're going to mention it again now that we can understand vector spaces in a more general form. So let's assume I have a basis B for a vector space and also another basis C for a vector space. If they are bases for the same vector space, then they have to have the same size. And what we mean by that is the number of vectors in B has to be equal to the number of vectors in C. And because of that, we end up with this fact. The dimension of the vector space is P, the number of vectors in a basis. So we know what a basis is. A basis is something that's linearly independent and spans the vector space. Well, if another set is linearly independent and also spans the vector space, then it must have the same size. Now, you can go ahead and prove that if you want, but we're not going to prove that. The proof, however, does come from the fact that we have the two bases span and the two bases are both linearly independent. So if they had different sizes, either one of them couldn't span or the other one couldn't be linearly independent. All right, so let's take some immediate observations. Let's say we have a basis B for a vector space. If I have this basis, if I had fewer vectors, then I wouldn't be able to span the vector space V. So if I had a bunch of vectors in a basis, I have, in this case, P different vectors. Any set with less than that many vectors can't be a basis because it would not span the vector space. It wouldn't have enough vectors to span the vector space. And on the flip side, any set with more than P vectors can't be a basis because it will be linearly dependent. Now, when I say any set with less than P vectors, I mean P vectors from my original vector space. P vectors from my original vector space V. All right? So if we have too few vectors, we can't span. If we have too many vectors, we don't get linear independence. All right? So we have to have just the right amount. Now, that leads us to the idea of dimensions, right? We say the dimension of a vector space is the number of vectors in a basis. That is true for all except for the trivial subspace. The trivial subspace we've seen before has only the zero vector. And a trivial subspace, a subspace with only the zero vector, we say has dimension 0. All right, there's no vectors in a basis here. By the way, another note is there are some infinite dimensional vector spaces. So if I think about the set of all polynomials, well, the set of all polynomials could have a basis which includes the number 1, the variable x squared. If we let all polynomials, we can just keep adding x to the third, x to the fourth, and so on and so forth, all the way out through infinity. So the set of all polynomials has actually infinitely many elements in its basis. All right, so if you, again, we let x to the n for any n we can dream of. The same thing for the set of all sequences. If you think about infinite sequences, an infinite sequence just is an infinite sequence of numbers. What would a basis look like for that? Or could we construct one? Let's go ahead and think about this. What we could do is think of an infinite sequence as the terms in that sequence, which usually we let A0, A1, A2, A3 be all real numbers. Let me make that a little bit bigger. There you go. So we have this infinite sequence goes on forever. Well, you could think of a basis for the set of all different infinite sequences as kind of like the elementary basis elements for R3 or Rn, where we have a 1 and then a 0, 0, 0. So we have a 1 in the nth spot and zeros elsewhere. Sometimes people start this at A1 instead of A0. Maybe that's a little bit easier. Let me do it that way. I'll start my sequence at A1 instead of A sub 0. I forget how I started it before, but basically you can think of a basis consisting of these infinite sequences where we have a 0, we have a 1 in the spot AI and zeros elsewhere. Okay? I didn't explain that well. Hopefully that makes all sense. Makes sense, excuse me. All right? So we could describe a set, a group of basis sequences where any sum, any linear combination of these elements can give us any sequence we want. All right? And you can see that there's going to be infinitely many of them because you can put a 1 in any of the spots that we want. Okay? I want you to push pause on the video and think about what the dimension of Rn would be, and think about what the dimension of polynomials of degree n or less is. And to do this, think through what the standard basis would look like for Rn, what the standard basis would look like for P sub n. All right, so hopefully you went ahead and did that. Think about, well, let's do a definite example. So if we think of Rn, let's, whoops, let's think of it R4, okay? We know what R4 is. It's the set of all four-dimensional vectors, and we can easily create a basis. In fact, we'll create the standard basis that has a 1 in one slot. So we'll call this E sub 1 usually, elementary elements of the basis. So R4 whoops, something happened there, can be thought of as linear combinations of the standard basis. I knew it. And the standard basis will be comprised of these four vectors, E1, E2, E3, E4. And you can kind of see how an infinite sequence kind of looks like an infinite vector as well. So R4 has this set, the set containing these four vectors as its basis, and therefore the dimension of R4 is 4. And you could argue that the dimension of Rn is n, no matter what value n takes on. All right? All right, so let's go and take a look at p sub n, so the polynomials of degree n or less. I'm going to do this for p sub 5. Remember the standard basis would be x5, would be the set containing x5, x to the 4th, x to the 3rd, x squared, x to the 1st power, and a constant 1. So any linear combination of these elements could give us a polynomial of degree 5 or less. Notice that in p sub 5, there are 6 different basis elements, and therefore the dimension of p5 is 6. Now you can see exactly how this is going to work in a more general term. If I wanted to talk about polynomials of degree 3 and less, well, I'd get the x third, x squared, x to the 1st, and then a constant. Polynomials of degree 30 or less, you get x to the 30th all the way down to x to the 1st, and then get a constant. So polynomials of degree n or less have dimension n plus 1. All right. So in general, we see that this has to be true. Let me go copy that. So Rn has dimension of n. Pn has dimension n plus 1. All right, so there we go. So P sub n has dimension n plus 1. R to the nth power has dimension n. Now, obviously, we're not going to be interested in just Rn or P sub n. We're going to be interested in lots of subspaces of Rn. For instance, we can calculate the dimension of the span of these two vectors. Now, let me just argue about what it's going to be. We have these two vectors, and so obviously the span of these two vectors is any linear combination of these two vectors. So if we throw v1 and v2 in a set, that set is definitely going to satisfy that that set is the span of that set is the space itself. Okay, so this vector space, which is the span of these two vectors, is definitely spanned by those two vectors. Now the other thing we have to know about bases is that a basis is a linearly independent set. Now with two vectors, all we have to do is check and see that they're not multiples of each other. And in this case, they're not. So these two vectors are linearly independent. So these two vectors are linearly independent. They span the vector space that I'm looking at. Therefore, these two vectors make up a basis for the vector space I'm interested in. And therefore, the vector space that I'm interested in has dimension of 2. All right? So the span of these two vectors has dimension 2 because these two vectors span the set, and these two vectors are linearly independent. Now, what you'll notice real quick is that this span of V1, V2, that is a subspace of R3. Notice that the vector space, the span, let's call the span V1, V2, let's call that H for just easy purposes. If we call this vector space H, the dimension of H we see here is 2, but it came out of a dimension 3 vector space, which was R3. So the subspace H had dimension 2, whereas the bigger vector space had dimension 3. And that has to be true no matter what H and no matter what V we deal with. If H is a subspace of vector space V, then the dimension of H has to be less than or equal to the dimension of vector space V. So if I'm looking at a subspace of R5, the dimension of that subspace is going to have to be 5 or less. If I'm looking at a subspace of polynomials of degree 4 and less, the dimension of that subspace has to be 5 or less, right? Because dimension of polynomials degree 4 is 5, so it has to be 5 or less. So if H is a subspace of V, then the dimension of H has to be smaller than or equal to the dimension of V. So let's think through. I want you to push pause on the video and think through finding some subspaces of R3 that have dimension 0, that have dimension 1, that have dimension 2, that have dimension 3. Think about how you would create a basis for each one of these and see if you can get maybe one subspace of dimension 1 or two subspaces of dimension 1, one or two subspaces of dimension 2, one or two subspaces of dimension 3, so on and so forth. Push pause on the video and see if you can create a subspace of each dimension within R3. Word document. R3 is the big vector space I'm dealing with. Now, when I'm trying to create a subspace with dimension 0, I should think bases. So what basis can I create that has dimension 0? Well, the only set that has dimension 0 is the set containing the 0 vector. So we would have to let my subspace be equal just to the set containing the 0 vector. All right, that's the only set of dimension 0. Okay. Now, what about dimension 1? If I wanted to find a subspace of R3 that has dimension 1, then what I'm going to do is I'm going to think basis. Let's create a vector. Doesn't actually matter what it is. So we're going to take one vector and we're going to say actually the span of that vector has dimension 1. So this 2, 3, 0 forms a basis for H, and therefore we have one element in a basis, so the dimension has to be 1. All right, now you could have chose any vector you wanted other than obviously the 0 vector, because the 0 vector doesn't make any sense to put as a span. So whatever vector you want, the span of that single vector is how I make a dimension 1 subspace of R3. Now what about 2? If I want a dimension 2, I need the span of 2 vectors because I want 2 vectors in my basis. We're going to have 2 rules for these 2 vectors. First, we can't have the 0 vector. Second, we can't have one as the multiple of the other. All right, we want independent vectors, linearly independent vectors. So here's an example of 2 vectors that would form a nice basis of a subspace of dimension 2 within R3. Okay, now you don't have to get fancy on this. If you want, you can make your vectors the columns of your standard basis for R3. Just take the first 2 if we want dimension 2. Now that's going to kind of be how we do dimension 3 as well. We're just going to take the span instead of using 2 vectors, we're going to use 3 vectors. We could use the standard basis vectors, but we want to make sure that whatever vectors we choose vectors which are linearly independent. So the span of the 3 span of the 3 standard basis vectors would be a dimension 3 subspace. Now, by the way, this would be dimension 3 subspace. Any dimension 3 subspace is all of R3 because we know it has dimension 3. So there you go. Another, if you don't want to use the standard basis, if you want to be a little bit different, by all means go ahead, use any vectors so long as they are linearly independent. You could plug these into your calculator and see that these are not, that these in fact are linearly independent. So there we go. That's the idea behind dimension 3, dimension 2, dimension 1, and dimension 0 subspaces all inside of R3. Okay. Now, let's argue something which we all should know and we've kind of been hinting at as we've been doing this. This is called the basis theorem. So if I let a vector space, whether it's a subspace or a vector space, all subspaces are examples of vector spaces. So if I just have a vector space V with dimension P, all right, and we want this to be a non-trivial vector space. We actually want P to be more than 0, so 1 or more. The trivial subspace is we want to ignore as much as possible. So we let a vector space be p-dimensional, all right? It turns out if you collect any linearly independent set of p vectors, which are within the vector space itself, it automatically has to be a basis. So think about that. What we're saying is we don't need to check the span because we have linear independence, and also the right number of vectors. That's what we were actually using in that when I was arguing that these 3 vectors have to be of dimension 3. I said, well, there are 3 of them. They are linearly independent, and therefore we're going to get the right span. Okay, so these 3 vectors, as long as they are linearly independent, which they are, you can check that, they are also going to span. Let me give sort of the reason why using this example. All right. So here's my idea. I'm claiming that those 3 vectors form a basis for R3. Go back up to the top. Just copy that. All right. Now, the reason I know is that I can check linearly independence. And if I check linearly independence, what would I do? I would row reduce the 3 by 3 matrix, which comes out of, I apologize, I hit the wrong button. So what I would do is I would row reduce the 3 by 3 matrix, which has column entries, those vectors in question. Now, once we row reduce that matrix, we get the identity. Now, the identity matrix, since we row reduced that, gave me the identity, has essentially 2 properties, right? We knew it was dimension 3. The R3 has dimension 3. But what I can see here is that each of these are linearly independent because we have no free variables. But I also see that because each row has a 1 in it, that it is going to span R3. In other words, if you did a linear combination of those 3 vectors, you could get any vector on the right. Again, thinking of solving the matrix equation AX equals B. All right, you can solve that for any B you want because we're going to have a pivot point not only in each column, but also in each row. All right, and that's kind of what the basis theorem is saying, but it's saying it for a more general case. It's saying that if you have the right number of vectors and you have linearly independent set, then I know it's automatically going to span the right way. And the reverse is also true. If I know that it spans in the right way, and I know it has the right number of vectors, I automatically know it's going to be linearly independent. Okay, because we're going to have enough pivot columns and pivot rows. And the corollary is that any set of n linearly independent vectors from Rn will be a basis for Rn. So all we need to do is make sure we have n linearly independent vectors. Just like in our previous example, I had 3 linearly independent vectors, and I saw that was a basis for Rn. Or if I have a set of n vectors from Rn, and the span of the set is Rn, then S is a basis for Rn. Okay, that's what I was explaining with my example from R3. We had this set. When we row reduced it, we saw that we had 3 pivot columns. That meant things were linearly independent. Therefore, we knew it was a basis for Rn. Or if I would have looked at it the other way, if I row reduced, we can see that we had 3 pivot points in each, we had a pivot point in each row. Therefore, the span of S would have been all of Rn. We had the right amount of vectors, so we have a basis for Rn. Now, once we see that, what we can do is we can figure out dimensions of subspaces of Rn's as well. So let's take the subspace that's defined here as H, and it's defined as the set of all vectors whose first entry looks like 5a minus 7b, whose second entry is b, and whose third entry is 3a. Now you can check that this is in fact a subspace. It contains the 0 vector, it's closed under addition, it's closed under scalar multiplication. Nothing big there. So this in fact is a subspace. So how are we going to find the dimension of that subspace? I want you to push pause on the video and try to find the dimension by coming up with a basis for this subspace. All right, so hopefully you went ahead and did that. Basically what you do is you look at these variables A and B, and for A, think of putting in the number 1 and B putting in the number 0. You're going to get 5, 0, 3 as the coefficients of A. As the coefficients of B, you're going to get negative 7, 1, 0. Now I claim that these two vectors with linear combinations can form all of the vectors in our vector space H, and moreover, that they are going to be linearly independent. Obviously, we have 2 vectors here. They're not multiples of each other, so they are linearly independent. The span of these 2 vectors obviously gives me H, therefore they form a basis. And that means that the dimension of H, I should have done this. So dimension of H is 2. All right. So why don't you go ahead and try that with this subspace of R4 and find the dimension of this subspace. All right, hopefully you went ahead and did that. Basically, we have our vector space H now. 3a plus b, b plus 7c, 4a minus 3b plus c, 2a plus 4b minus 2c. So we want to find linear combinations. So let's write the natural 3 vectors that would form linear combinations. To create the vector space, we just take the coefficients of a, the coefficients of b, and the coefficients of C as our three vectors. And the one thing we do need to check out is we need to make sure that these are linearly independent. We know that the span of these three vectors will give us every vector in H because that's how we built it. So all we need to do is double check that these are linearly independent. One way you can do that is take your calculator, create a matrix. Now this was a 4 by 3 matrix. If you remember back from previous doing this, you do have to sort of add a dummy column in there of all zeros so that the thing works. But you just go and take 3042 as your first -3 4 as my second, and then as my last vector, it was 0 7 1 -2. And then again, unless I add this dummy row of, or excuse me, not dummy row, dummy column on the right hand side, it's not going to row reduce real nicely. So I just take, and let's see if row reduced A, and sure enough, these, since I have 3, each column is a pivot column, so all 3 of these are linearly independent, or this set of 3 vectors is linearly independent. All right, again, ignore that last column there. So these 3 vectors span the set, they're linearly independent, and therefore the dimension of this H is 3. Okay, so there we go. Now I want you to do one more and think through this one. All right, so we do this one. Basically, if you did it the same way, what you'll start with is 2 vectors. These 2 vectors we know span H. Whoops, I got double H there. These 2 vectors span H. However, if you notice, these 2 vectors are scalar multiples of each other, so they are linearly dependent, as a set is linearly dependent, and therefore I can eliminate one of them. Okay, so I can eliminate that 2, 2, 2 if I'd like. And so actually, the subspace H is spanned by a single vector 1, 1, 1. And so the dimension of H is 1 because I only needed one vector in my basis. So basically, we just need to figure out, well, now that we have a set of vectors that spans H, can we find the ones that are linearly independent? Now, what if we have something like this? H is the span of these 4 vectors. We want to find the dimension of the subspace. So the idea is that we take these 4 vectors and we start them out as a set of 4 vectors, and then we're going to toss out any vectors that are linearly dependent. Okay? Now the way to see that is to utilize the calculator once again to take and create a 4 by 4 matrix row reduce that, and then see which are linearly independent based on the pivot columns. Go ahead and push pause on the video and try that on your own. In about about 5 seconds, I'll come back. All right, so what I did is I took my matrix, I plugged in this 4x4 matrix, then I'm going to go and do a row reduction, that was a different A, on my matrix A. And what I have here is that columns number 1 and 3 are pivot columns. Therefore, I have 2 pivot columns, and the other 2 columns represent free variables. So I have 2 pivot columns. That means that the span of this set could have been generated by just the first vector and the third vector. And so the first vector and the third vector would have been generators for my set, and therefore the set containing this first vector and the third vector is a basis for H. So the dimension of the subspace is 2. I want you to try this one on your own. Find the dimension of the subspace generated by these 4 vectors. All right, hopefully you went ahead and did that. When I created that matrix with a 4x4 matrix with these vectors as the columns, and then I row reduced that, what I got is 4 pivot columns. And therefore, all 4 of these vectors are linearly independent, and therefore the dimension of this subspace is in fact 4. Okay, so linearly independent, all 4 vectors, dimension is 4. Now, I've mentioned this in chapter 2, but I'm going to mention this again. When we deal with subspaces, obviously the null space and the column space of a matrix are subspaces that we're generally interested in calculating and finding. And we're going to be interested in calculating the dimension of the null space, the dimension of the column space. Now, we're going to be so interested in that we're going to give these special names. The dimension of the null space we call the nullity, and the dimension of the column space we call the rank. Okay, and this is these are universal terms. When I say we, I mean the community of mathematicians. We all call the null space dimension the nullity, and the dimension of the column space is the rank. So let's find the dimension of the null space and the dimension of the column space for this matrix. Go ahead and push pause on the video and see if you can come up with that on your own. All right, hopefully you've done that and you've taken your time and figured out the dimension for the null space and dimension for the column space. Now, how you do that? Well, you start with your matrix A, you row reduce it. When you row reduce it, you get this matrix. Now, what we're going to see is that columns 1 and 3 are the pivot columns, and columns 2, 4, and 5 represent free variables. So we see these 2 pivot columns, and what that means is that all of the other columns can be written as linear combinations of my first column and my third column. So if I'm talking about the column space, the set of all linear combinations of these column vectors, all I really need it to form the basis is columns numbers 1 and 3. So the basis for my column space is going to be my original column 1, which was -3, 1, 2, and then my original column 3, -1, 2, 5. And all other columns can be written as a linear combination of those two. That means that the dimension of the column space, or the rank of A, is 2. Now for the null space, also I'm going to be looking at the reduced echelon form of A, and I'm going to say, well, what vectors can I multiply and get out 0? Okay, so think of this in terms of an augmented matrix where I just left off the 0 column on the right. What that would mean is x1 minus 2x2 minus 1x4 plus 3x5 would be equal to 0. x2 would be free. x3 plus 2x4 minus 2x5 would be equal to 0. And then x4 and x5 would be free. Let me write that. So as far as looking for the null space, what I'm going to do is I'm going to start with the general solution. x1 is equal to 2x2 plus 1x4 minus 3x5. x2 is free. x3 can be written that way. x4 and x5 are free. And then in for the basis, I just put a vector representing each free variable. So I put x2 is equal to 1, and x4 is equal to 0, x5 is equal to 0. That'll represent one vector, and then I let x2 be 0, and x4 be 1, and x5 be 0. That'll represent my second vector, and then my third vector I get when I take x2 is 0, x4 is 0, and x5 is 1. We've done that enough. I hope that makes sense. So let me pull out the coefficients on x2's. That'll be 2, 1, and then 0, 0, 0. So for x2, we get the vector 2, 1, 0, 0, 0. I might not be able to see that. All right, so that's the vector there. Uh-oh. So there's a little bit of blip there with the Microsoft. But we get the vector 2, 1, 0, 0, 0 as my first vector. That represented the x2 being free. The coefficients of x4, I'm going to get 1, 0, -2, 1, 0. 1, 0. Oops, I didn't look at that. -2, I apologize. So 1, 0, -2, 1, 0. Okay, coefficients of the x4. Coefficients of the x5, -3, 0, 2, 0, 1. So -3, 0, 2, 0, 1. Okay? And we can see that this set of three vectors has to be linearly independent, just based on what we know about null spaces, but also you can see that because in order to get the x2, the second entry, to be 0, you'd have to, if I wanted a linear combination of these three elements to be 0, I'd have to multiply this first vector by 0. In order to get the fourth entry to be 0, I'd have to multiply the second vector by 0, and in order to get the fifth entry to be 0, I'd have to multiply the third entry by 0. So the only way to get the 0 vector is by taking 0, 0, 0 times all three of those vectors and then adding them up. Now I say all that to just say that is a basis for the null space. So we see that the nullity of our matrix A has to be 3 because we have a basis of size 3 for our null space. Now, once you do that, if I'm just looking for dimensions, I really didn't need to go ahead and find the basis itself. So let's make a quick observation here. I actually don't need to find the dimensions. We see that the nullity of the matrix is going to be the number of free variables in the equation AX equals 0. And the rank of a matrix is the number of pivot columns. So the nullity is going to be the columns with the free variables. The rank is going to be the number of pivot columns. And therefore, I don't even actually have to find a basis for the column space of A or a basis for the null space of A in order to find the rank and the nullity. So I would like you to do that. Use free variables and pivot columns to find the dimensions of the null space and the column space of A for this matrix. Go ahead and push pause on the video and see how that goes. So hopefully you went ahead and did that. I am trying to double check and make sure I wrote everything down right so I don't make a mistake, but sometimes that happens. All right, so what we would do is we would tape this gigantic matrix into our calculator. There it is, I put it in B, and then we're going to row reduce B. When I do that, I get this. Notice that there are going to be 1, 2, 3 pivot columns, and 1, 2, 3, 4 free variables. So in this situation, I use matrix B. I don't know why I did that on my calculator, but basically the rank of my matrix, I called it B. Did I use that in the PowerPoint slides? No, I called it A in the PowerPoint slides, so I just, for some reason, threw everything off. Let's go by the letter A instead. The rank of my matrix that I got. Dimension of the column space. Remember the column space, we had 3 pivot columns. So the dimension of the column space is 3. And by the way, the basis would have been columns 1, 3, 5. And the nullity of the matrix A would have had to have been 4. I ended up with 4 free variables, columns 2, 4, 6, and 7. So those 4 columns represent free variables, and so the nullity is going to be 4. So rank is 3, nullity is 4. I want you to go ahead and try this example. Find the dimension of the null space and the column space of this matrix. Push pause on the video and do that. All right, so hopefully you went ahead and did that. Basically what I did is I put in a matrix A into my calculator. Now, don't forget, if you tried to row reduce using just 3 columns and you didn't add that extra dummy column, it'll give you an error. So we have to add that extra dummy column, but again, remember, we pretend it's not there. Okay, and then we go ahead and row reduce our matrix. Oops. So go ahead and row reduce matrix A. And notice that you get 3 pivot columns. And remember, this dummy column doesn't count. Now, if this, again, this dummy column is basically this just there, so our calculator doesn't give us an error. So we pretend that this dummy column doesn't count. So we have 3 pivot columns and no free variables. So the rank would be 3 and the nullity would be 0. Okay, 3 pivot columns means that the column space of A is dimension 3, and no free variables means that the null space of A is dimension 0. And there you go. So that's how to deal with dimensions in Rn. And by the way, just as a little side note, last time what we did with those coordinate mappings, we could have mapped any polynomial space into Rn and found dimensions of subspaces of polynomial spaces. All right, so if we wanted to do that, we could have done that. I'm sort of avoiding it right now just for the sake of ease. So that is it for this section. The next section, we'll come back and we'll get ever closer to done with chapter 4.